energy to AI for materials for carbon capture and conversion. And it's my pleasure to introduce Dean Jennifer Chase. And like our previous dean, so she is the dean of the new College of Computing, Data, and Data Science and Society. Mark is the dean of the, is about the dean. Is he actually already elected? Well, anyhow, he's probably going to be the dean of the College of Engineering starting on July 1st. And like Mark, Jennifer is a scientist on her own right. Both of them are sort of highly acclaimed scientists, but of relevance for this one may be that Jennifer actually was named one of the 20 most influential players in California tech. Other people like Musk is also one of them, so Jennifer is in good company here. Okay, with that, Jennifer will chair this session.
Okay, great. So full disclosure, he's my husband. So he had to say something nice about me. Okay, so the last session was entitled AI for Materials, and this session, I think, is entitled Carbon Capture and Conversion. But as you will see, this is also very much a story of AI for materials. We're going to have 3 fantastic talks, one on materials for carbon capture, one on materials for carbon conversion, and one on really how to do self-driving labs. So again, a little reminiscent of what we saw last time for all of these applications. So the first speaker is Omar Yaghi, who has, I think, over 60 international awards. So it's becoming a little ridiculous, actually, Omar. So he has the Wolf Prize and the Tang Prize and the Vin Future Prize. And every couple of weeks, it seems, or maybe a couple of months, he wins another prize. So let's see, I have to find out. Oh, yes, a week or two ago, he won the inaugural International Union of Pure and Applied Chemistry's prize for sustainable chemistry and many, many other prizes. He's a professor of chemistry here. And full disclosure, he's my collaborator. So let's welcome Omar.
For the introduction, and I know Christian is your husband. He said nice things about you. I'm not your husband, but I still say great things about you. So I'd like to share with you our experiments with AI and where we are, especially for materials discovery, as it also relates to carbon capture. I have a few slides on how to also make drinking water out of air. So the first slide that I want to show you is an illustration of a MOF. It's a movie. If you could just play the movie, it'll take a few seconds for it to start. But MOFs are highly crystalline materials, meaning that they are ordered, they have ordered structure, and their structures have been characterized and are characterized by single crystal X-ray diffraction. And if you zoom in, to the eye, they appear like granulated sugar. If you zoom in on one granule, you will see their beautiful network-like structures made from intersections or hubs that are inorganic, linked by organic to make open structures into which our idea is to compact gases just like bees on a honeycomb. Bees may fill very large volume, but if you have a piece of honey, which could be the moth, they assemble around that and compact them, compact gases such as hydrogen, CO2, or water without having to use pressure or low temperature. And so that's the idea with MOFs. And well, almost any element metal in the periodic table has been used to make a MOF. The metals make metal oxide units that they are then joined by organic units. And the organic units could be as simple as lactic acid, which is in milk, citric acid in orange juice, or petroleum-derived linkers such as terephthalate and so on. And they could be as small or as long as this one, where you could make MOFs that would take your proteins in, or they could have very exotic shapes, but each imparting a different property, whether it's a photophysical property or a catalytic property, onto the framework. So the other powerful thing about MOFs is that since you can adjust which building units you're using, you could also adjust the metrics of the pores. You could make small pores or larger pores, and here's a great student who didn't stop after making the first and second one, kept going, and made the largest pore material ever accessed in crystalline form. And as I said, these can have they can also incorporate biological molecules, making them interesting for biotechnology applications as well. So it's really, we created almost a periodic table of reticular compounds, and the challenge is, is trying to figure out what you want to make. And if you do, you can combine shapes on this side with this side, and this table will tell you what you're going to make. And almost 90% of the time, this is correct, which is much better than any other chemistry. And the reason is that these geometric building units do not undergo changes during the assembly process, so you can actually predict how they are going to come together. And you can see all kinds of shapes on this side. Molecules can have triangle, square, tetrahedron, and so on and so forth, and you can combine them with other molecules. These could be inorganic, these could be organic. You know, the amazing thing about MOFs is that, let's say I make this structure out of triangles. I could spend my whole life working on this, and not only because it has a rich chemistry itself, but also because I can adjust all the metrics. I can make larger units, functionalize those units, make catalysts, make carbon capture materials, and so on. So each one awaits a long chemistry that would be developed. And you can also combine those shapes with more complex shapes, and you can keep going, right? And some of the younger people in the crowd don't feel despair. There's still a lot of work to be done, especially when it comes to the complex shapes. So what I want to say here is that if you can think it, we can make it. Okay? It took us 35 years to develop the chemistry. And the reason I'm interested in AI, and I collaborate with Jennifer and Christian extensively as part of the BIDMaP Institute, is that when you assemble these building units, the very first thing a student experiences is that they're not highly crystalline. And so they spend 2 to 3 years doing trial and error in terms of finding the conditions under which to crystallize them. That's where AI is becoming really, really important. And so very early on, we showed that these can be made in multi-ton quantities in our collaboration with BASF. They can be made cheaply and all the things that you need. So what I want to talk about today is what we've done in what I call the air economy, which is carbon capture, water capture from air. You can get hydrogen from water. That's Peidong will talk about that. We already take oxygen out of the air, and we also take nitrogen out of the air to make fertilizer. So today I want to show you 2 examples of carbon capture and water harvesting. Okay, so the best CO2 capture material from air is here. And it's a COF, it's not a MOF. It's actually an all organic material we call covalent organic frameworks, where the constituents are linked by some of the strongest bonds known in chemistry, carbon-carbon double bonds and carbon-nitrogen double bonds. It took us over 10 years to figure out the chemistry of this framework, but now we can make it routinely and in high yield. We can functionalize it with those amines that Jeff Neaton was talking about. to trap CO2. And this is the experiment that convinced me that there will be life on our planet, that we can capture the CO2 that's causing climate havoc. And that's this experiment. Here's the CO2 concentration, Berkeley air. It's around 450 ppm. This is the humidity level, and this is the material taking up CO2 from the air. When you pass Berkeley air into the solid or into the powder of this cough, it traps all the CO2 that's in the air. You get no CO2 on the other side of the material. That's how effective it is, and we find a relationship between water and the CO2 uptake. The more humidity in the air, the better the uptake. But when you look at one humidity level, the behavior is constant throughout the experiment. This is the best performing carbon capture material for air capture, for CO2 from air, that has ever been reported, and these are the parameters that convince anyone that this is commercializable. So at scale, we want to take the 1,100 gigatons of extra CO2 from the air, and using our material, this is the parameters, this is capacity is 2 millimole of CO2 per gram of cough, and each cycle takes 10 minutes, CO2 in and then CO2 out, that's one cycle. And to get this job done using this cough, if you have a plant that deploys 100,000 tons of cough, it will capture half a gigaton of CO2, okay? But if you have 700 plants or so in cities around the world that have a population of 1 million or more, it will take us only 3 years or so to take away all that extra CO2 out of the air, okay? And then, I mean, that's your quanta. You can divide it in the way you want. If you want just 200 cities that are 2 million or greater in China, US, and Europe, it'll be 11 years. So it's doable. And what's convinced me that it's doable, not just that the properties that we have obtained and the stability of the material, but also that the chemical industry is used to this kind of scale. I mean, the world produces globally 200 million tons of sulfuric acid, okay? Coughs are a lot safer than sulfuric acid. They're solids. They're non-volatile solids. So we have the chemical industry, we have the ability to work on that scale. And so I think the carbon capture problem is solved. Scientifically, it's solved. It just needs the will of society to say this is a crisis that we want to invest in. Okay. I think for water capture, I'm going to skip it, but we can make MOFs that take up water from the driest of deserts and make drinking water, okay? With no energy input aside from ambient sunlight. And the water is pure, it's clean, and the MOF not only works at dry desert, if it works in this case, in Death Valley, it will work in Singapore. Okay, it will work at all humidity levels. In places where you might have a lot of humidity, but the water is not clean, you could use it also to trap water from not just arid, but humid areas. And for the water harvesting from air, these are where we are. 1 ton of MOF with no energy input aside from ambient sunlight will give you 3,000 liters of water per day, every day, for about 6 to 7 years, for the lifetime of the electronics of the device, okay? And if you want to electrify it, it's 60,000 liters of water per day, every day, for 6 to 7 years. Okay, so this is, again, another problem that we are addressing, and it looks pretty impressive and close to commercialization. Okay, so I want to share with you, this is the sort of the main point that I want to communicate with you today concerning the use of AI for discovery of new materials and for optimizing properties. And this is a result of 2 years of work and collaboration with my colleagues, Christian and Jennifer, and postdocs that are working in BIDMaP. You can think of it as two cycles. One is AI computational cycle, and the other one is experimental cycle. And typical chemist will input either a chemical formula, you have building blocks, they have chemical formulas, or a desired property that you want, maybe CO2 capture. And using this generative model based on diffusion models, you can get some initial structures. Many of them, hundreds of thousands, can be generated. And I'd like to say that Teo is really in charge of this project. He's a BIDMaP fellow. And you get hundreds of thousands of structures. Some of them are not so chemically viable. These are weeded out by doing a quantum level kind of geometry optimization like DFT and ML machine learning force field. You get your optimized structures, but then you do even more. You try to weed out the structures that are not going to be porous, since we are looking for porous structures if we are trying to do CO2 capture. And this involves Monte Carlo sampling, a machine learning type predictor, and ultimately a human check. Then using this, we get out some synthesizable structures. Okay, synthesizable structures have gone through, are the building units available? Are they widely available? Are they cheap? Do they require dangerous solvents to make, or can we make them in benign solvents? So all of that can be incorporated into this input. And this gets picked up by an LLM that does the synthesis planning, as was described by Gabe earlier. And this synthesis planner gives you, in our case, we're looking for conditions under which you could crystallize the material. And like I said, crystallization is 90% of our time as chemists is spent trying to crystallize our compound. And it's one of the most long-standing problems in chemistry. So it will spit out some reaction conditions. This could be temperature, solvent type, all those things. And so we subject it to an automated synthesis using robotics, high throughput, and we ensure that, in fact, what we make is reproducible. So we take extra care to make sure that every time you do this, based on those specific conditions, that you'll be able to do it, because later we want to scale it up. Then you have some synthesis outcome crystals, and we use multimodal characterization using automated imaging, X-ray diffraction, spectroscopy, some technique that we can automate, and then we get our characterization data. This is then subjected to an ML-assisted data analysis to recognize the crystals, to identify the phase in crystallography, assign spectra, and now you've got your potential good structure, okay? We compare this to what we are targeted back here in our synthesizable structures. And if it's good, if it's satisfactory, then we go to a property. We say, okay, now I've got my structure, can it do this or that? And if that's satisfactory, then this is more measurements, right? To check whether the material has the properties you need. That would be your platform output. If it's not satisfactory, then you put it in the data set and you go through the cycle again. Okay, and so using this kind of AI computational experimental combination is quite powerful, because you get to put in the good data and the bad, and the experiments that didn't work, the things that's all embedded in the cycle. So what's the result of this? The result is that we chose a subclass of MOFs called ZIFs. Never mind what they are, but they're basically zeolites that are made from metal organic. Our initial data set was about 2,600 reactions. We use 8 different linkers. And the result of this was that our discovery rate was twice that of my lab, okay? So you can think of this in the following way, that for the last almost 20 years, people have been making ZIFs, okay, and they made, 200 ZIFs, and we can do double that in less time, okay? So, and some of these structures are obvious in the art, meaning that I would look at them and say, oh, okay, they're new, but I could have guessed. But some others are completely new that I wouldn't have been able to guess. And they're very interesting for applications such as separating alcohol from water, which is a very difficult thing to do because they're azeotrope. The other result was that based on those cycles, you can come up with some sort of exotic linkers that we haven't thought about. And maybe they will lead to a new class of materials that I call hypoorganics, where you have the least amount of CH bonds per linker. These hypoorganics are emerging as very, very interesting for carbon capture. One of them is already capturing carbon dioxide from the air, not from the air, but from cement plants in Canada, and it's being commercialized. So using those, the students are able to get those linkers that were put out by those cycles and actually use the experimental cycle to make the corresponding MOFs. In no time at all, within 1 week, the students were able to get them in crystalline form. So that's the kind of transformative thing that's happening in the way we do chemistry in my lab. The things that have been taking years are taking weeks. And somebody mentioned already LLMs, and we have been experimenting with ChatGPT, and my students have done and published work on using LLMs, text mining. We were among the first to do this in the chemistry community. They are some of the most highly downloaded papers in chemistry. But today I want to focus on the research group as a last example. I know I have 1 minute left. So here's a typical activity in my lab and in general in chemistry. That is, you imagine a structure. We imagine this structure. It's a cough, and we deemed it interesting for potentially harvesting water from air. Okay, it has hydrophilic centers, hydrogen bond donor to water, and lone pair acceptor to water. So I'm sorry, I should have said hydrogen acceptor and hydrogen donor. So it would take my students, who are absolutely brilliant, okay, it would take them 2 to 3 years to crystallize this material. They may be making it in 5 minutes, but to actually make it in crystalline form, it would take them 2 to 3 years. And using ChatGPT as a multi-agent ChatGPT that does a lot of the stuff, like read the literature, summarize the literature, guide. This is the PI, guiding the experiment, analyze, synthesize, do the programming of the robot, and so on and so forth. Do the 3D printing of the glassware or the materials that we use for the experiment. And in doing this, the student is able to go from a non-crystalline material to a crystalline material in the course of about 84 experiments, okay, using the cycle that I have, or using ChatGPT. This could be done now. In those days, where there was primitive conditions in ChatGPT, now this could be done in less than a day. But in those days, it took us 2 weeks. So something that would take 2 to 3 years is reduced down to 2 weeks. Okay, well, this is what I want to share with you. I think I like to say that AI is transforming the way we do chemistry in my lab, and we are not looking back at all. And almost all my lab is blending AI and computation into their work and using those cycles that I mentioned. I want to mention that we're trying to commercialize this and accelerate discovery, as I've shown you in the preliminary results. We created a startup called Amatics. You can look it up. I want to acknowledge my wonderful students, the funding agencies and sources, and thank you for the invitation.
Hey, this Is this live? Yes? Okay, so I should say that I gave my speakers 20 instead of 30 minutes to allow for a question or two in between. I also forgot the most important thing to say why Omar won all those awards, because he is the inventor of MOFs, COFs in the field of reticular chemistry. Okay, so that was, that's why he won all those awards. Okay, so are there one or two quick questions? Okay,
Thank you. Thank you so much. This was so inspiring. You spoke about the problem of carbon capture and how that's solved, and it's a matter of really society choosing to invest. What are the problems that you see? Is it a policy problem? Is it a matter of funding? Is it a matter of, recently I've seen a talk by Tom Chi, and he was talking about surface. So the surface you cover to capture carbon. So are there technical problems? What are these kind of barriers that we have to work on?
We already have plants that capture CO2 out of the air. Just the materials are not very good. The materials break down and they cause problems and so on. They don't cycle as well, right? Because you're pushing a lot of air through the material. So what the problem we solved is that we made robust materials that are going to withstand years and years of cycling without having to replace them or replenish them. So that, I think that that's an important advance. I mentioned the comment about society is because when we decide that we have a crisis, like when we did with the pandemic, we put in $1 trillion to fix it, and it got done, okay? And when we decided we had a housing collapse that's throwing our economy out of order, we decided that that's a crisis, and at the time we put in $900 billion, almost another trillion, to put us back in order, and it worked. Well, this one is even better because you're investing in a process that potentially could be a future economy as well. You're adding to our economy by capturing CO2 and everything that goes. Professor Peidong Yang will talk after me, and he will show you that CO2 perhaps could be converted to a high-value product. Well, that's another economy. So it is worth the investment. But we're not going to be able to do it for free. Okay, you can't just emit for free and capture it for free.
Okay, okay. If you can answer a question in 1 minute, Omar, then
Sure.
we can.
Yeah, sure. So it seems like you're mostly focused on MOFs and COFs, sort of adjacent chemistry is zeolites, and it seems like you've experimented with something similar with ZIFs. Is there any particular reason that you're not focused on zeolites, and do you see any room for zeolites in carbon capture or pure water generation?
No, there's absolutely no room for zeolites because zeolites hold onto water so tightly. You have to heat them up to 300 degrees overnight to remove the water, so that's not economical. For CO2, they're lousy, and the reason we developed MOFs in the mid-1990s was because every zeolite chemist wanted to make zeolites from metal organics. The metal was going to provide them with better catalysis, and the organic was going to provide them with better way of tailoring their pores so they can do very specific reactions. Well, we succeeded in doing that, and that's MOFs. So zeolites are great for refining petroleum, but their days have passed because now you can make materials precisely by design on the atomic and molecular level, and with the AI, it's unstoppable. Yeah.
Okay, let us thank Omar again. And Omar also set up our next talk because what are we going to do with all this carbon dioxide, with with the 1,100 gigatons of carbon dioxide that we capture? And so our next speaker is Peidong Yang. He is a distinguished professor here and co-director of the Kavli Energy Institute. He too is the recipient of many, many prizes, a MacArthur Global Energy Prize, Lawrence Prize, ACS Nanoscience, and so on and so on. And he is renowned for many things: nanowire synthesis, artificial photosynthesis, solar to chemical energy conversion. And here, we really are excited in BIDMaP about the fact that we will not only be able to pull carbon out of the air using AI, but we will also be able to convert it into something incredibly useful. So let us welcome Peidong Yang.
Okay, thanks, Jennifer. I think Omar set up the stage for me to talk about CO2 conversion. So really, for the CO2, Omar already mentioned the CO2 capture and conversion. We're talking about really at a gigaton level. Okay? And I am going to also talk about how can we turn this CO2 into a new industry. That's our future chemical industry, and potentially operate at the terawatts level. And of course, for today's symposium, I will also talk about how AI and the machine learning can help us in this sort of transitioning of this new chemical industry. As of today, of course, the global power consumption is roughly about 16 terawatts, and that's causing many of these CO2 emission problems for the past 100 years. And of course, we're expecting this power consumption is going to be increased, right? It's maybe by 2050, this power consumption will be doubled, okay? And along that process, of course, there will be additional CO2 CO2 emission into our environment. Okay, so that's this number is something to keep in mind. We're living in a society that requires energy at a terawatts level. And every year we're talking about the emission of 35 gigaton into our environment. That's every year that's happening, of course, from all the sectors, from our power plant, from our manufacturing site, cement, transport, every sector. Okay, of course, chemical industry as well. Okay, and that's another number to keep in mind. And that basically causing the CO2 concentration is increasing. And it's still increasing every year by 1 or 1.5 ppm, okay? And we will see that trend for the probably next 20, 30 years, okay? We're moving towards the carbon neutral sort of stage, maybe at 2050, right? So this is what the Paris Agreement is talking about. In the next 20, 30 years, we want to head into this carbon neutral. And eventually, by end of this century, we're getting into the carbon negative society. But that being said, the next 20, 30 years is still carbon positive. Okay? We're still emitting CO2 into this environment. That's why the CO2 capture and the conversion business is so important at this moment. We really need to think about, of course, for this particular symposium, we need to think about materials for CO2 capture. Omar already solved this scientific problem. And in the meantime, we certainly want to think about how can we utilize those CO2 and turn that into chemical energy, turn that into useful chemicals. And in the meantime, of course, decarbonize all the sector we're talking about. Okay? And by doing so, of course, what we're talking about is potentially we're going to transform the current chemical industry. Eventually, we're using CO2 as our feedstock. Okay? And that is going to be probably another $1 trillion industry we're talking about, right? Okay, so that's why the CCUS, the U side is, of course, we can do the carbon capture, do the sequestration. That's one route. But the U is also very important because that's the chemical energy storage sector. That's the basically base that you can really utilize this sort of waste chemical, CO2, and utilize the renewable energy. Maybe that's from solar, maybe from the wind, and store all those renewable energy into the chemical, actual carbon-carbon bond, which is as of today, still has the highest energy density, right? Okay, so how can we do that? Okay, and what is the sort of scientific or technical challenges we're facing? Okay, what do we want to do? We want to basically start with CO2, water, and the renewable energy, right? And somehow we want to have this chemical reaction. Okay, we want to turn that two very simple chemicals, CO2, water. Okay, it's actually turns out to be two simplest chemical, but it's two chemicals that's very, very difficult to activate. Okay, and as that turn into maybe sort of chemical energy storage, making fertilizer if we put the nitrogen over there. And of course, we can also think about using CO2 to produce these high value added chemicals or even pharmaceuticals, okay? And not to mention the high energy density towards this aviation fuels, right? Okay, so everything is about in the middle. Catalyze the chemical transformation. And every chemical reaction will need a catalyst. Okay, that's the key sort of ingredient for this whole carbon CO2 conversion to work. And how to do that? Of course, there are many different ways to think about it. Traditional industry uses thermal catalyst. Okay, but of course, we know the thermal catalyst give us CO2 footprint. Okay, so I would say in the past several decades, people are looking into how can we use solar energy directly to drive the CO2 conversion. And of course, another sector is basically the so-called PV, the solar panel plus CO2 electrolyzer approach. Okay? So let me briefly show you. My lab has been working on this artificial photosynthetic system for now more than 2 decades now. Okay? Starting from the earlier days of Helios program and towards the first DOE Energy Hub, Joint Center for Artificial Photosynthesis. This sort of artificial photosynthetic device is a device that's really mimicking natural photosynthesis. Typically, this sort of device has a photocathode, a photoanode. You don't need add additional sort of bias. Okay, all you need is sunlight goes into this device. Okay, so that the two photoelectrodes will power two half reaction. Okay, just like in the green leaf, right? You have CO2, water goes in, sunlight goes in, then you make carbohydrates and oxygen. So this sort of artificial device that's developing here at Berkeley is doing the same thing. So we can basically, CO2, water goes in, do this one step, this so-called solar to chemical energy conversion and storage. Okay, CO2 goes in, then somehow the C1, C2 intermediates will come out, plus oxygen. Okay, and that's the sort of the photochemical diode concept we're dealing with over the past more than a little bit over 2 decades. These electrodes, okay, these electrodes looks like solar panel, okay? And if you, nowadays we're making sort of pretty much at a 6-inch wafer scale on the photocathode and the photoanode side. And this is where the chemistry happening. It's that looks like a sort of photoelectrodes, solar panel, but they run chemistry. Instead of the PV is solar to electricity, this device actually, when sunlight goes in, CO2, water goes in, it basically produces chemicals for you. Okay? So that's the sort of the photochemical diodes that's mimicking the photosynthetic activity within the green leaf. That's one way to do it. Okay? In one step, basically, CO2 stop converting to C1, C2 intermediates, while the chemical energy of the is stored in those bonds, based on the renewable energy, right, from the solar. Another popular approach, of course, that's also there are many startups in this sector as well, is based on the concept of renewable energy, maybe from PV, solar panel, and the wind, right, and hook up with a CO2 electrolyzer. Okay. And that basically where you can do the same thing. It's a 2-step process. It's the solar energy or renewable energy to electron. Then electron pump into the CO2 electrolyzer, do the chemical transformation for you. Same thing, in many of those cases, CO2 goes into C1 and C2 intermediates. Okay? 2 approaches. One is 1 step, another is 2 steps. They both have pros and cons. Both approaches moving both in the academic and the industrial sector. And here are a couple of examples that are coming out from my lab. You can see that we can, these are sort of several examples you can see. We can make format, okay, in like 1 liter level, 1 molar scale. Acetate, C2 intermediates. These are all made out of CO2 using our artificial photosynthetic system. Then, of course, these process, okay, the artificial photosynthetic system or PV plus electrolyzer approach, we don't have a way to one step to turn CO2 into a very complex chemical yet. Typical strategy is CO2 go into C1, C2 intermediates, then utilize the existing biological catalysis or existing chemical process to further upgrade them. And here I show you 2 examples. We can upgrade them into making PHB. Okay, those are 1 gram of polymer, biodegradable polymer over there, or from CO2. We can even make sugar. This is glucose. Okay, glucose out of CO2. And this is a true mimic of natural photosynthesis, right? Nature is making glucose or carbohydrates, and now we have a chemical process through this our artificial photosynthetic process to make sugar out of CO2. Okay, so those are all possible. Okay, so now, okay, those are basically in the lab. We are developing these sort of artificial photosynthetic device. Step by step, you make the catalyst, you put on the photoelectrodes, then do the system integration, testing. It's, as Omar already pointed out, it's a very, very sort of long process. You have discovered catalyst, you put it into the device, you test it. We are doing that for the past 20, 25 years. Okay? So we want to accelerate that process. What's the key sort of scientific issue we need to sort of really push this field forward? That is the whatever we're dealing with, whether it's the photochemical diodes or PV plus CO2 electrolyzer or water electrolyzer, the key thing is the catalyst. Okay? We need a catalyst that satisfies these conditions. Okay? Non-precious metals, low oil potential. The catalyst, as we know, any reaction, you need a waste energy to activate CO2. In this case, activate CO2 in the water. So we need ideally, we need a catalyst operate at a thermodynamic potential. Okay, that's happening in many cases in the green leaf. Okay, and of course, we want high selectivity, especially for CO2 reduction. We need high production rates. Okay, and of course, for long-term operation, we need a long-term stability. Everything we need basically an electrocatalyst run at least for 2 very, very important half reactions. One is CO2 reduction, one is water oxidation. Okay, those are the two half reactions where we are very, very interested in, and also it's critical for this new industry. Okay, these are 2 simple sort of molecules over there. So very recently, we were talking about basically launch this activity in BIDMaP. Okay? So this is accelerated, we call it ICAT. Okay? And I think on the AI side, the most important character is I, intelligent. Okay? It's not as artificial, it's the intelligent part is the most important. So it's, we're thinking about really trying to accelerate the discovery sort of process. Okay? You can see this is having a couple of steps. Basically, the first step is a machine learning-based design for low overpotential, high selectivity CO2 catalyst and the water oxidation catalyst. These are the key bottleneck that really is slowing down the whole sort of community, and also in terms of the commercialization of these either CO2 electrolyzer or our artificial photosynthetic system. So in that aspect, we need to worry about many things. We need to worry about these nanoparticle, which composition to deal with, okay, phase diagram, what sort of surface structure is important, and what is the surface structure over potential correlation. Okay, those really require sort of AI and machine learning to tell us. And of course, we started with automated high throughput catalyst synthesis, and followed by machine learning-based structural characterization and high throughput electrochemical testing. Now, if in using that process, basically we hope to accelerate the catalyst discovery using a closed loop sort of scheme. And once the a better catalyst is discovered, we can immediately integrate into our system overall artificial photosynthetic device. Okay, so I will give you a couple of examples. Actually, 2 examples where the AI and machine learning can help us. One example is our recent collaboration with BSF. I notice we have some BSF colleagues here today. This is an effort that we're trying to basically solve one of the key problems in the water oxidation side. Okay, in the water electrolyzer, one of the key catalysts, uranium-based catalyst. Uranium, of course, is very expensive. We don't have enough storage on the planet Earth to drive the whole water electrolyzer sort of industry. So we want to replace uranium with other elements. And one element coming out is ruthenium. Okay? Ruthenium actually is a good electrocatalyst for water oxidation with even lower overpotential compared to uranium. However, it's not stable. Okay, so our approach is using this high entropy alloy-based idea to stabilize these water oxidation catalysts. Okay, trying to utilize active site of ruthenium, but meantime using high entropy effect to stabilize the whole thing in the electrochemical condition. But in the high entropy alloy, okay, usually we have 5 elements, 6 elements in these nanoparticles. Okay, which elements we want to select to start with. Okay, so here's one sort of a small step we are taking. Our BSF colleague actually started using this ML. I think Jeff Needham talked about this in the first section, ML IP. Really to use this method to calculate, survey the periodic table, calculate this so-called short-range ordering between these 2 elements. Okay, you can see a range of these different elements calculated in the SRO. And those are in the negative side. That's telling you that these elements can be mixed together. If in the positive side, those elements will face separate. Okay? But for high entropy alloy, we're trying to sort of pinpoint which element we can start to mix them together. Okay, in the nanoparticle form. Okay? So here's one example. You can see actually you can survey all those exotic elements, including those non-trivial elements like scandium, titanium, chromium, which is very, very difficult to make in the nanoparticle metallic form. Okay, but that tells us, okay, you can see a regime of these multiple elements where we're going to plug in our experiment efforts. Okay, so we're starting to basically, I think that little square over there is something our initial sort of testing is going on. Okay, in those 5 elements mixing. And I think we have lots of sort of efforts to be done over that direction as well. Okay, so that's one basically guidance in terms of which composition, which structure we want to target. Then, of course, you will have to worry about automated synthesis platform. At Molecular Foundry, we have a couple of robots that's used to make these metal nanoparticles in high sort of throughput manner. Okay, that's one platform we are going to have access. And very soon, this high entropy alloy nanoparticle deposition system is going to be installed in my lab. This is 5 elements that we can basically do the simultaneous sputtering. And this is a system that we're designed to make those non-trivial high entropy alloys. Make like putting in scandium, titanium, chromium elements, which in the conventional solution synthesis you are not able to make. Okay, so this is going to be very powerful deposition system to use. Okay, okay. So now discovering catalyst is I don't think it's an easy task. Okay, because the electrochemical process is highly dynamic. This is not a static sort of structure over potential reactivity correlation. These catalysts and the electrochemical process are constantly evolving. So we do need, again, in this case, is a big data assisted multimodal operandal characterization and the electrochemical condition. This using, you can see a range of these facility, 40 STEM. I think in Maria Chan's talk about 40 STEM as well. X-ray absorption, XPS, all these different beamline technique will give us a huge amount of data and operating conditions so that we can identify these structural descriptors. Okay, it's probably not going to be 1, probably going to be 5, 10. So that's the data sort of collection process. That's related to the coordination number, related to the crystal structures, surface facets. Many of these structural descriptors need to be identified. Just give you one quick example. For the 4D stem and the electrochemical bias, you can generate lots of these data, okay, in the 2D scan and all these electron diffraction pattern. Easily one section, within like 1 hour, you have generated several gigabits of a data set. Okay, all these diffraction pattern on these very well-established copper nanoparticle catalysts. They are evolving under electrochemical bias. So that diffraction pattern is also evolving. So we collaborate with Emo Hans group at Rice University to do this image recognition and the clustering. Okay? And that tells us which facet or which direction, what's the crystallinity correlate to the reactivity. Okay? And this is basically the machine learning-based image grouping, and that tells us all these which grains is correlated to high activity of CO2 conversion. And this very soon this paper will be in print in Nature Catalysis. And follow that. Okay, follow the structural dynamic characterization using machine learning and AI guidance. Of course, there is the next thing is high throughput activity screening. Okay, we are going to use this scanning electrochemical cell microscopy to look at the composition over potential correlation. Okay, and that's another high throughput characterization technique that we need. Again, if we identify a good catalyst, that will be placed into the electrolyzer. Okay. Now I want to basically close by using 2 slides I borrowed from my colleague Henry Edward from the LISA, that's the Energy Hub Phase 3, just show you how the chemical industry can be transformed. Okay? And this chart, this petrochemical sort of chart, tells you almost all the petrochemicals are contained in 95% of all the goods we are using, okay, for all of us, okay, from your cell phone, from the aviation field, everything polymers. And of course, you cannot read all these small fonts. Of course, current industry is basically based on this crude sort of fossil fuel, right? But intermediates, you can see, it's all C1, C2 intermediates. Okay, that's from the fossil fuel. But I think the key message here is all those intermediate C1s like ethylene, C3, C4, even methanol, formaldehyde, all these C1, C2 intermediate can be produced from CO2 and the water and the sunlight. Okay, so that's the new industry that we're looking at in the next sort of another 20, 30 years. Okay? And here you can see that if we replace that, you can sort of remove all these carbon footprint in many different sectors, plastics, aviation fuels, e-methanol. Okay? And that, of course, fundamentally changing the foundation of the existing chemical industry, and that's a new chemical industry we're talking about, maybe when we're reaching the sort of carbon neutral society by the 2050 time frame. Okay? So with that, I want to conclude. Thanks for the invitation. Okay? Thank you.
Okay, so I think we have time for a question. Is there anyone who can ask a question after that incredible vision of the future? Okay, since you haven't asked I don't want to, but okay, since you haven't asked a question before, I'll give this to Christian, who I just met.
Okay, so I have a question sort of in the realm, since we're here about also applying this in the future and stuff. One could imagine that there will be for quite some while resistance to actually implement this new industry. Would be there some way to think of if finally everything collapses to implement it really fast? Or is it something where we need to build it up over 50 years?
Yeah, that's a very good question. The chemical industry transition will not be overnight. It's not going to be overnight. It will take several decades, okay? So right now, all these CO2 electrolyzer, all these artificial photosynthesis systems, they are coming out from lab. Now we're seeing many of these startups is starting to do related, sort of trying to commercialize this methodology. But that will take actually industry to basically take in this new technology. And I'm a believer that is the existing oil industry needed to transform their chemistry. Okay, so it's their business opportunity. And it's only these oil industry can do that because they have the money, they have infrastructure. All they need to do, think about is transform their feedstock. So, but that will take decades to do that.
Okay, so maybe, Alexis, a quick question, and then we'll go on to our next speaker.
So, quick question. One of the products you can make relatively selectively from CO2 is ethylene.
Mm-hmm.
And even if you imagine Faraday efficiency of 100% to ethylene, at 2 to 3 cents per kilowatt hour, it's uneconomical just on the power basis. It's not until you get to a penny a kilowatt hour. And the projections for that to happen, I've looked at this, are somewhere beyond 2035. Now,
yeah.
How do we get industry to adopt that? Because if you could make ethylene, you can build up a lot of what you showed on one of your next to last slides.
Well, I think this is a tough question for basically for the scientific community as well. That's why I'm keep saying the identify key catalyst here is the key. Right now, of course, you talk about ethylene production, its cost is too high. Why is too high? It's because of over potential is too high. Okay, we're wasting all the time. You are seeing some startup or people are talking about claiming CO2 electrolyzer doing great stuff, converting CO2 to ethylene, but catalyst is still the key problem. Okay, that's why we want to have this ICAT accelerated discovery efforts. If you have a catalyst wasting 1 volt to convert a CO2 to ethylene, of course it's not going to work. So here, in order for this industry to work, we do need a sort of disruptive catalyst to appear. And for that disruptive catalyst to appear, I feel doing our sort of traditional way, try and error, is too slow. Okay, this is a common message today, right? We need a fast, we need a faster. Okay, so we need a catalyst that's operating at a thermodynamic potential. If the catalyst is operating at thermodynamic potential, I think cost will come down. So that's, of course, it's related to also the renewable energy cost has to be come down too.
So that's the vision of ICAT, actually, for BIDMaP, right? How do we accelerate the production of catalysts so that the cost will come
I
down?
want to briefly mention for water catalyst, water oxidation catalyst, and the CO2 catalyst, in the past 5 decades or so, over potential, the needle on the over potential hasn't moved a single bit. That's the problem.
So
a little bit.
hopefully AI to the rescue, we'll see. Okay, so we have had 2 well-established luminaries, and now we're going to have a talk from a future luminary, Shijing Sun, whom I just met at the NeurIPS conference in December, and this is already our 2nd time having her down here to give a talk. She has an absolutely beautiful vision of how to build an autonomous laboratory for energy science. And let me just say, she has gotten one very recent recognition, the Royal Research Fund, RRF, Royal Research Fund Award for 2025 for this work that she's going to be telling us about. Let's welcome Shijing.
Thank you. Thank you for the kind introduction, and it's absolutely my honor to be back in Berkeley and share my work and to be in the same room with the leaders in our field. I feel very honored to be here. Thank you for the invitation. I'm going to share our work from a mechanical engineering point of view. I'm currently working in the mechanical engineering department, and we are from University of Washington in Seattle. And the punchline of my talk is that I believe everyone in this room you probably already have the resources you need to build an autonomous lab. And I'm going to explain why I believe so. Starting with, I want to remind everyone why we are here. So the fundamental challenge, both in academia and in industry, about materials R&D is we actually have an infinite search space across time scale, across length scales. There are so many potential good materials out there. At the same time, I don't need to remind everyone here, we have the urgency. We want to accelerate the materials innovation that we can match the urgency of resolving our climate change challenge. And here is just a show of how temperature globally have been changing over the years. We're actually not doing that bad in terms of the AI help. In fact, there are so many new materials being discovered computationally in the past decades. So one of the examples is back in 2023, we saw a Google DeepMind discovered over 400,000 hypothetical materials and put them in materials projected database, which is kind of locally here in Berkeley. It's very exciting. And note the number there. At the same time, 1 year later, as experimental scientists, we celebrated our 300,000 number of a new material, not even new, just in the record, the material structures in the ICSD database with the experimental database. So note the difference. This is in one go, we can have the computational, predicted materials, which is the 400,000, and experimentally, over the decades, after decades of work, we actually made 300,000 in that magnitude. So there's a widening gap between how computationally we can discover hypothetical materials supposed to be really good for our energy technology and how experimentally we can realize it. So the field I'm in is really we want to build autonomous labs, or self-driving labs. That's kind of a word we use within our field, is that instead of bench chemistry, maybe we can have the robotics to do high throughput synthesis. Instead of sample by sample studies, we can kind of blend in the automation in characterization across length and time scales, of course. And instead of just relying on our domain experts analysis, we bring in data science and machine learning. So if you really think about the three things on the right, and that leads to a new ecosystem, where we are studying how, by having the automation in the laboratory and bringing the artificial intelligence in, if we scientists have a brilliant idea about tomorrow's clean tech, we can quickly, using this framework, to accelerate the realization of such ideas from the laboratory to the market. So the first part of my talk is really about how do we automate a traditionally manual bench chemistry process. Of course, as a scientist, I want to work on the most impactful topics, and it's not a surprise. I wanted to work on a carbon capture, and we start to look at the ways to automate metal organic framework synthesis. From early talks, we've heard the importance of this class of nano porous materials. So we just took one of the standard recipe, and here it's just typically how you would perform a bench chemistry in terms of most synthesis of metal organic frameworks materials, with the potential for carbon dioxide capture applications. And it didn't take us that long. In fact, it's within a few weeks, we're able to program our liquid handling robot to perform the same experiment. And we use X-ray diffraction to confirm that it's indeed the MOF74 MOF crystal structure we want to make. And on average, an hour of manual work has been removed. So we use robotics. But what has been challenging is that the access of X-ray diffraction, as one of the example being the advanced characterization, is not something we just have in line next to our synthesis bench. So here is the kind of common challenge. How do you combine the characterization you need to your synthesis, to the system you are building? So more and more often, we start to look for proxies. So in this case, is an example where we use optical microscopy as a proxy, where we can distinguish whether a MOF crystallization happened or we made set products, which is not what we want. And with that, we can automate the characterization by using like a high throughput microscope. So in this case, it's an example where we use like proxies to increase the throughput of characterization. Of course, with images, that also leads to the next advantage is that we can quickly start to implement computer vision to help us extract information from images. So our group now have like a number of different algorithms, but essentially all what they are doing is we start to automate the information extraction from the characterization techniques. And in this case, very clearly, we get to see the metal organic framework crystal forms, and we extract them, and in fact, the whole process becomes very enjoyable. So here we can track the crystallization outcomes with quantitative measures. We have single crystals, we see some of the overlapping crystals, we see some of the clusterings, and of course, you get all the statistics within seconds. So these efforts really kind of formulate the idea. Instead of understanding one synthesis conditions, we can perform synthetic screening and quickly build databases. And in this case, we can quantitatively measure what is the small tweaks in synthetic conditions to the crystallization outcome. And all of this has been automated. And what you essentially see is that we start to have the precision synthesis platform in ways like the synthesis, the characterization, and the data analysis has been automated. So it's worth to notice the image analysis just by using computer vision, often with machine learning models, embedded. In our case, we demonstrate over 35 times acceleration in terms of the time it takes. But to me, the most exciting thing is actually not the acceleration part. It's actually now we have the robot doing the synthesis. We have the robot going through the characterization. It aids that hours of the time that are freed up for scientists to do other things. That to me is the most valuable. So because now we can have pretty much start to automate all the individual process in the laboratory. Scientists are free to work on more creative problems or think about new challenges. So if we really take this path to the end, what would happen if you just start to automate every single process in your lab? So this is kind of one of the more advanced self-driving lab. And in terms we have a much larger scale of synthesis. We have the transfer robot to take the sample from one station to the other station. And in the characterization station, we have, again, another robot take the sample, put it into the characterization station, and then get the data. And the whole thing is autonomously operated. So what you see here is basically the videos from PNL. It's the National Laboratory, which is my collaborator, and they have this robotic laboratory operations for energy storage. So at this point, you may say, great, including the sample transfer, every single step has been automated. It must be we can generate a lot of data. That should be probably the next step we can do. And we are going to use all this data to train machine learning models. So the second case study here is we had this collaboration, and we're let's use the robot to just improve the yield of a molecule that is actually good for redox flow batteries. And we quickly realized even with just 4 dimensions, we were just putting a design space where we want to find the optimal conditions to improve the yield of our reaction. That is how many runs of the video everyone just saw need to really screen over. So that comes to the question. Even with all the resources we have in terms of robotics, our goal is not necessarily to screen over all the conditions, because this will take us just by running it over 16 years. And a lot of the experts in this room in chemistry may say, well, I actually know some of these conditions will never work. It's just a waste of time. You are just collecting data for the sake of collecting data. So it's really the message I want to convey is that's where AI become very powerful in locally controlling the robots. So I want to design the instructions to the robot. So the idea in this region is I want to design the brain for autonomous labs. It is very important because we don't want to just generate data. We want to learn from each run of our experiment, and then let the robot to improve upon this. So like over the past like a few years, like our lab has been doing a number of different type of models, trying to kind of take what like the experimental results are and then give the next suggestions. So the key method behind like this design is definitely active learning. So we start with like very little data, and then we do round by round by round. And in this example, with the constrained batch-based optimization, after 3 rounds, 45 experiments, instead of those like over like 150 million, we start to see the convergence where the optimal region starts to appear. And this is very powerful. And in fact, not only in like what I just showed, like in terms of the examples with the molecules, we also extended similar idea. And this is in collaboration with Dr. Caroline Sutter-Feller here in LBNL. We also use like active learning in terms of like making thin films. And this AI-driven robot again achieved like basically converge, like we have learned the space with less than 1% of the actual sampling. So that is basically saying like we have like potential 100 times like acceleration in terms of like the learning with like just like with the AI-driven experimental design. And you can certainly see with like this like a little small data, but it's sufficient for us to build the synthesis property relationship like a map, and that can be coupled with in situ characterizations for more advanced study. So like at this stage, you will say, hey, this is really great, but you are collaborating with national lab, which obviously we love to. But how do I have one in my own lab or in my own company? So that's kind of like the third part of my talk I really want to talk about is how do we, instead of accessing all these like robots cost millions of dollars, how can we build new autonomous systems very quickly? So the key here as a mechanical engineer is that really we can introduce modularity in lab automation. So the plug and play is like we can use it to guide our design. So here, the 3 videos basically just show like the 3D printed like laboratory parts my students designed, printed, and integrated in our liquid handling robot. With this, if you want to do hot casting, you put a heater, you design a unit. We want to measure the photoluminescence. We design like a 2-motor system with the like samples being screened. So we did a case study, and in this case, we have our liquid handling robot, and we keep putting different like modules, and each module is what we like self-designed and with different like characterization capacity, and then we have like our like Gaussian process like regression model, kind of like a machine learning part, and suggest the next experiment. And then say we use in this case, let's do like the porous guides as a model system, because like it's kind of like a little bit complicated, like energy conversion material, and like I thought it would be interesting to look at it. So okay, so we are going to start with going back, yeah, just our self like designed hardware, and then we are going to see if we can teach it to make porous guides, either specific porous guides with specific crystal structures. Round 1. Well, these hardwares doesn't know much. Like actually, this is the experimental points, and the yellow is the target, is the material we want to make. And then we started to like put our AI like algorithms in, and we say, how about you learn about it? We tell you like what like the fingerprints you should be looking at in our like characterizations, and can you learn from it? Round 2. Like the model say, hey, here are some experiments you should make, and they start to make some of like the materials like we wanted to make is closer to the target. Round 3, round 4, round 5, round 6. So you see it's like the active learning methods round by rounds with our AI-driven materials, AI-driven models. We start to see it's like we get closer and closer to the target, like a porous guides like we want to make. So the key here is really that with just self-designed hardware, no prior knowledge of chemistry, no knowledge about like what makes a perovskites. It takes 6 rounds of like a data collection for the AI models to figuring out this is how to make like a 2D perovskites. And guess how long it takes for these 6 rounds? So like with our system, all this data were taken within a day. So like you see, it's like so now we are entering era where like for mechanical engineers without chemistry background, and as long as we can digitalize what we are looking for in terms of our like target materials, and we encoded them into our like active learning models, and we transfer these models to our robots, and round by round, they can quickly converge to our target. So this is really like promising, but I told my students, it's not fast enough. I want to be faster. How can I test our AI models faster than this? And my students quickly saying, well, we don't even need a liquid handler. We don't even need those modules you asked us to design. I'll just build an autonomous platform from scratch. Okay, this is where we started with. And this is the next stages. And like, so my students started to like put together the hardware with the idea of all these electronic boards in the end put on our robot so we can have our like AI models to speak to the robot. And when I show like this, how long it took us, sometimes like the audience will be surprised. Oh, so indeed, so this process from nothing to we actually have like a fully operated like 3D like a printing frame with our like autonomous system, it took like 2 weeks. The reason of that is because like this hardware frame is part of like the open source hardware initiative. So by having good documentations, like just like how we share the open source software across like the world, we started to have the community to share open source hardware. And that's kind of like answering one of the early questions like in the session, like in our software, like we have so many like design experiments, can we implement them in the laboratory? And my answer is yes, because like there's so much talent within the like mechanical engineering, the electrical engineering, and we can pull these like efforts together to democratize autonomous science. And a few months later, after we built this robot, now it's like this is a video showing like we are mimicking the liquid handling robot we bought, but this time it's just like all like the hardware and software designed in-house. It doesn't like look different, like if it is just an automated experiment. But actually, this is autonomous experiment because each time the liquid handling robot will make like an experiment, mixing some different colors, the solutions, and then the camera will take a photo, and the photo gets sent to the AI agent, and the AI agent decide on what is the next set of the synthesis. So this is a real-time decision making. So which means every time we go to take a video, it's going to be a little bit different because the algorithm will decide on like a different way of making the synthesis based on the real-time characterization feedback. Everything in one system, and the overall cost is less than $3,000. So closing remarks. So what I want to mention is state-of-art self-driving labs. We are confident to say we already are in the regime of having 10 to 100 times acceleration in terms of our synthesis and characterization steps. And with like our AI embedded into our algorithms, we demonstrate autonomous synthesis and characterization across a wide range of materials, class, and also characterization techniques. To most important message I want to share with everyone is that it's not like you have to wait until you collect tons of experiment data to start. The beauty of AI is that you can learn as data is being collected. So iterative learning really helps with small data, especially in the experimental world. The second message I want to give is we also want to scale our autonomous lab approach for the industry to use it. How to do it quickly is we have the modular system prototyping design is the way to go, because before we invested in like the large-scale robotic systems, these autonomous systems really helps to identify what automation works for your specific chemistry and materials project. With that, I'll stop. I want to thank all the founders, collaborators, and my students who actually did the work. Thank you very much.
Okay, do we have one or two questions for Xiling before we convene the panel? Yeah. Oh, no, you're getting a mic.
I got a mic. Hey, Xiling, thanks. Thanks for the talk. So on the sulfonation project there, am I misunderstanding? All variables were continuous?
That's a very good question. So it is a continuous in terms of design space, but it's not continuous in terms of the instrumental limitation.
Okay, but
Yeah,
the design space is continuous. It's just the implementation, it is not.
Exactly, and there's, I'm sorry I didn't have time to go into details, but actually there were also multi-step synthesis. There were like also the mixing part where we have a different batch size to the heating part, which is constrained by the number of heaters there.
But that's still continuous, right?
Exactly, yeah.
I'm asking that because we have in the room here Herman, that is the CEO of a company called Actinary that has been developing Bayesian optimization processes for these kinds of continuous and categorical variables for a while. And my question here is, when it comes to design space that we're doing, do you think of ways that we can then modulate hardware in order to explore that faster?
Yeah, it's actually a great question. And this is exactly what we've been working on, because we found that actually all the times in terms of specific projects, the off-the-shelf Bayesian optimization, batch-based implementation, constraint Bayesian optimization, we tried all different ones. None of them actually work exactly with our hardware. So because the throughput differences, and also we need a kind of interdependent sequential steps of this. So we really want to collaborate potentially to look for new algorithms allowing us to modify our hardware based on the information AI said, oh, this is the batch you should design. Because we can modify hardware. We just need to know what is the most information efficient way to do that. Yeah.
One more question, or should we pivot to the panel? Why don't we pivot to the panel? Okay, great. Yes. So I invite all of our speakers up here. Okay, so I have a few questions. With each of these questions, I am going to start with one of the three of you, and if the others of you want to add something, you can or not. So, Omar, what are the biggest gaps between AI-generated predictions and experimental validation in chemistry and material science, and how can we better integrate the two to accelerate discovery? We heard a lot about computation, we heard about experiment, we've heard about putting those together, but what are the biggest gaps?
I mean, one of the things about chemical systems is that very slight variation give you tremendous change in properties. And so I think that that's an area that requires a lot of attention, and it's not clear yet how you would do that with high throughput. That's why there was a term there, precision in the high throughput synthesis, that I put on one of my slides. So it turns out that if you want to make a CO2 capture material, water harvesting material, or anything, or a catalyst that does what Pei Dong is talking about, or Alex has mentioned, very, very slight variation in the electronics of the system. They could be very subtle, metric changes of almost a tenth of an angstrom could make a big difference in these systems. And I'm not sure we have a way to capture that yet. But I have no doubt that we will in the future, yeah.
Okay, Shiling, do you want to comment on that?
Yeah, like I agree very much. Like in the ways, because we always say with the robots, we can have like a increased precision and reproducibility, but that actually have some hidden caveats, because the higher precision we want the robot to be, often that comes with the slower like steps, and also it comes with the higher cost. So I think there's a trade-off there, like the data quality we want to get, and what is the experimental like capability we have.
Pei Dong, would you like to add in? Yeah.
Yeah, I think for the, just quickly mentioned previously, for the catalyst design, that's even more challenging, because it's for all these electrocatalysts, it's not really about a static crystal structure. It's dynamically evolving oxidation states, how these interfaces formed. So it's very heterogeneous. How can you link these big data, like from the 4D STEM, X-ray absorption, XPS, towards selectivity over potential? That's very, very challenging. Okay, hopefully AI can help us to solve this problem.
May I add one short comment, Jennifer, thanks. Chemists are very good at taking something and optimizing it and making it perfect. What we're not good at is finding where that thing is going to be in this massive space that we all have to reckon with. So I think what AI is doing that making me very excited is telling me, look in this corner where nobody has been looking, and then once you've hit that MOF, let's say, there are maybe old-fashioned ways of optimizing, at least for now. But these I can imagine will be automated in the fullness of time.
Right, we're not going to just look under the lamppost for our keys under the lamppost of our biases and our previous experience. Yeah.
Yep. Thank you.
Okay, Pei Dong, I have one for you. It kind of came up in your talk and in the questions that followed, but let's see if you want to add to it. To have a real impact on climate, we have to be able to scale these technologies. And how close are we? And I think you answered some of this, but and Omar got a question to this effect too. How close are we to really being able to do this at scale?
Do you want to start with capture first, then I'll talk about conversion?
Well, I think the question of capture, as I said, scientifically it's solved. I have no doubt that these coughs will be made very cheaply. We proved that with MOFs, that they can go down from $50,000 a kilo to less than $5 a kilo. So with coughs, it's a similar thing. The thing that this new chemistry does is that when you discover a structure that has a specific property that you really need, you can go back to that structure and change it around from different building units, cheaper building units, without affecting the property. That's really the hidden message of reticular chemistry that I almost never talk about, but it's there, and this is the work that the hallmark of the chemistry. Now, to scale that, you need to scale up coughs to hundreds of thousands of tons. Well, BASF is already scaling MOFs to, I saw a room as large as half of this room full of one MOF that a couple of men were moving it with rakes, moving the powder. So their chemical industry is quite powerful at scaling things, okay, and quite powerful at making things cheap. I do think that the societal acceptance of carbon capture is absolutely necessary to make this a reality. It's not enough that we have 4 or 5 plants in Europe and North America doing this. This is going to be in 700 cities, 700 plants. That requires a societal will on a global scale to do it. So I think that's the challenge that I see.
Yeah, hey Don,
Yeah.
you had a lot of thoughts on this, but it would be great to hear you expand.
So I think in my talk, we both mentioned this is gigaton level sort of chemistry or industry. I think on the CO2 conversion side, I don't want to paint a very rosy picture, okay? So it will take decades, okay, many decades. That's why I basically forecast like beyond 2050, beyond 2070, these CO2 conversion technology, one day it will be play a significant role in the carbon negative sort of society. I'm not so sure before the carbon neutral, they will, what's the percentage of these new chemists will play in the industry? There's a couple of things. Scientifically, I think we are in the same situation. Scientifically, we're demonstrating these chemistry worked. Okay, we can use renewable energy to convert the CO2 water into whatever we want. Okay, but their efficiency, their energy cost, their sort of overall operating cost is still a problem. And that reduced down to the overall system integration. What's the key elements here we're talking about? Energy cost, renewable electricity. Can we drive that down? I mean, many people will say one day these renewable electricity can be as cheap as free, okay? Then you don't want, that's not going to happen. I see somebody is shaking her head. Okay, if that's happening, of course, that energy waste on our catalyst end, that's eliminated. But if it's not happening, of course, you need to worry about overpotential of the catalyst. Okay, you don't want to waste energy. Okay, and of course, then there is selectivity issue. Alex mentioned even nowadays the best catalyst, they can do many sort of interesting chemistry, but selectivity is not ideal. Okay, so that's why I think yes, it's promising, and I think I'm confident that in the sort of maybe post-carbon neutral society, these CO2 conversion chemistry will play a significant role. And during the next 20, 30 years, chemical industry have to start to play a bigger role here, to start sort of utilizing, sort of incorporating this new chemistry into their daily operation. Then over the years, then the fossil fuel chemistry will come down, CO2 chemistry goes up. Then that's a similar thing, like just carbon neutral towards carbon negative.
Yeah, I'm going to wear a different hat here as someone who used to work in industry in Toyota before I joined University of Washington as a faculty. And so when I was working in automobile industry, I noticed like the automation level is actually very high. It's like, actually as a society, we've been using robots for decades in the industry to scaling up different processes. And the idea is like now kind of we are reimagining this scaling up process with artificial intelligence or like with intelligent system to help us to design of these processes. And maybe you two does not agree with me, but I personally think like scaling up challenges in terms of formulating into optimization problem for AI to resolve is easier than a scientific discovery project. Because like if we have the very firm goals of this is the stability we need, this is the over potential we want to minimize, then we can frame it as a multi-objective optimization problem and see if AI can help us in taking us to the next step. So I think often it's when we do not have a clear, like a numerical goal, then like AI is still trying to figure out how it helps us to explore.
So I know I'm very hopeful and excited that ICAT will accelerate the discovery of new catalysts, and it would be transformative, really, because as you say, we've been stuck on, with old methods of catalysis, and and then also having all kinds of geopolitical implications of certain catalysts. So hopefully AI can help us there. Xijing, I want to ask you, what is the role of humans in AI-driven labs, and to what extent can we envision replacing scientists in material science and chemistry? And where will human instinct remain essential? So where are we still, or are we going to need any humans at all? And if so, where?
Yeah, I want to start by saying I think the idea of having AI and automation in scientific research is not to replace us, but to empower us, right? But during the process of empowering us, of course, we want to give some of the more tedious work that's easier to give to like the robot. But I think in my mind, when we talk about the human in the loop, AI-driven discovery, it's not necessarily that human in the loop is an intermediate towards human out of loop. It is a human in the loop by choice, because we want to be in the loop. And why I think it's important, I think number one, the tool development is like the AI and the robots actually still far away from actually achieving the scientific goals we want. And secondly, they are the more strategic, ethical, safety considerations. I think that would involve a lot of the human judgment for AI to actually make meaningful, positive impact to our scientific research. So I think humans.
I'm going to ask a follow-up question to all of you on this, and then we'll turn to the audience. For young people here studying chemistry, chemical engineering, materials science, mechanical engineering, what advice would you give to them to future-proof their degrees and their careers?
Okay. I'm going to say some provocative things just to enhance the discussion. I do think that our higher education system involving research optimizes for productivity and less creativity when you really think about it. Imagine students in our lab who are very creative, but their productivity is less than those who just follow a blueprint of success. So I think there has to be a shift we need a quantitative measure of creativity, okay, that we all agree on. I don't know what that is, but whether it's how many papers you publish in high-impact journals, I don't know if that's the right measure. But we need a measure. If anybody can come up with a measure of creativity and in research, you're going to make a lot of money, or you're going to make a lot of people very happy, and you're going to transform our innovative culture. So with that in mind, I would say if you're a new student and you're interested in AI and interested in fortifying your future and making sure that you're going to be relevant and you're going to be marketable and you're going to get the best jobs and the highest salaries, I would say try to get out of your ecosystem. Okay, for example, if you're in my group doing XYZ, go on your own and bridge over to other departments. Go to computer science and say, this professor doesn't know anything about programming or anything about ML. I want to learn from the professionals, right? Go to mechanical engineering and learn how you could build your own robot. I've had students that do that, and they are amazing, right? So their rate of development is exponential. Their rate of creativity becomes really, really great. So I would say that there is a limit to what a PI can give you, okay? And we are programmed to try to get you to think outside the box. But you're in charge of your own project, and you have, especially in Berkeley, is a wonderful environment where you can go to different departments, and you as a student can talk to other professors, right? To other postdocs. And they're willing to meet you and discuss these exciting problems at the frontier. So that's my advice.
Peidong?
Okay. Follow up on that. I think the latest sort of emergent AI materials, AI chemistry, is another great example of how science is being done these days. It shows you that the cross-disciplinary sort of type research is more and more important. In the older days, all the scientists are sitting in their own silo, like chemistry, organic chemist, inorganic chemist. They just do their own thing. They don't interact. Okay, and of course, in the past couple of decades, within the departments, people start to interact, and then more recently, people from different departments do interact. Like my group would interact with the physics department, MSE, and the latest with CDSS. Okay, so this is another great example that I think in the future, all the scientific opportunity lies in these interdisciplinary type of research, and the AI indeed should help in sort of develop the new generation of chemistry and the materials discovery.
I just want to add an advertisement. Caroline Safar-Feller and I are organizing summer school at the Molecular Foundry annual user meeting in August on robotic synthesis and machine learning analysis. Please do look at the Molecular Foundry. I'll be back in August, August 13th to 15th. Please sign up.
Awesome. Now perhaps we should turn to questions from the audience, if there are questions. Yes?
Yeah. Okay. Thank you.
Oh, okay, and then...
Yeah, sorry, I already had the mic. So, regarding the previous question here, that was about the role of humans, and then also with Omar's take that I think you said you thought it was controversial. I think it's natural. But here's the thing. I will push back on your answer simply because I have given that same answer. I think we need to be thinking very seriously about the possibility that market pressure will be one that it will try to push out people from knowledge work that we do. And I think that we need to take that seriously and talk about what happens. And that's my point to the panel, to not just accept this premise that I also have been one to say, well, it's okay, we're developing these tools to help us accelerate things, but actually the market pressures may turn against the entire community.
I think you deserve to answer first.
Yeah, okay, great. Firstly, I think it's like a very valid discussion. Are we kind of like, fooling ourselves, saying we'll be fine, just trying to be optimistic, or like it is the hype makes us feel the fear before it comes. So it's a very valid discussion. So I think I agree with you because I also work on automations. Like a lot of my work is to like automate and putting people out of loop. But I guess what I can say now is what we currently see is like for fully automated systems, we are lacking that scientific purpose. And as long as like at the moment, it is the scientist, it is like the human like needs, the human curiosity is the driving force. So we are still in control of these tools in terms of shaping what we want the tools to do and how we want to develop it. That's currently what I see, because the fully autonomous system without that scientific motivation and drive hasn't really led us to like a true discovery yet.
Yeah, may I comment on that question? I agree with you about the potential that these AI systems will replace humans in probably 99% of what we do, and probably highly desirable, especially in the when you go to get your driver's license renewed. You can see that it's probably best to just automate that whole process, take the humans out of the loop. But I think that there's something about humans where we are eternally creative. And the thing is, you don't need more than 0.0001% of the population to be creative, right? And so that creativity will save us a lot of trouble in future. That's why I keep statistics work in our favor, because you don't need each one of us to be creative, right? It would be nice, but then who would build stuff, right? We will all be architects rather than builders. Yeah. Well, all right. Yeah. So there you go. No, but yeah, I agree that humans are going to be out of the loop very quickly, because we make a lot of mistakes and we're biased and we're obnoxious. You know, look at me. There's a lot of stuff that we can automate and make things simpler. Yeah.
Okay, thanks. I have a question that is related to Jennifer's last question, and because I know that Pedro and Omar are one of the best chemists in the world, and Shijin is the rising star in our young generation, and I really want to ask related about AI plus traditional chemistry and materials question. What is your expectation for the future student? Because I probably will get into academic position, and I'm gonna have my own group, own student, and collaboration, and worldwide. I really want to know, what do you think about the AI area education for the new generation of students, PhD student and postdoc, and
In chemistry.
in chemistry, combining traditional chemistry materials plus AI in the new area?
Pedro, you haven't said anything. Maybe you go first.
Yeah, I think that's a very, very, very deep question here. Sometimes I also start to ask myself, will these traditional disciplines still exist? Let's say by the time we're getting to carbon neutral, 2050. That's the first question, right? I mean, nowadays, okay, in the past many, many decades, chemistry evolved, okay? I mean, from, as I said, initially it's very, very focused in sort of organic, inorganic, physical. Now it's very, very sort of cross-board. I mean, take Berkeley as an example, right? It's just very, very sort of cross-disciplinary. So now the AI is inside. But AI seems to be sort of revolutionize the way we're planning experiment, the way we're collecting data, the way we're analyzing these data. Will this happen one day, let's say 2050, when in our undergraduate curriculum, we no longer need to teach undergraduate inorganic chemistry, physical chemistry? Is that possible? Or by that time, basically, these things will be, you can just learn through AI tools. If that day is happening, then I don't know. I mean, that's then we're talking about many of us will be replaced. I don't have an answer. Okay, I personally, I think yesterday I was having dinner with Gerber Cedars. Okay, we are talking about the same question. I think he immediately gave me answer. is within 50 years, it's unlikely that AI will replace all these traditional. Unlikely. Okay, like 100% replace the traditional sort of teaching of traditional discipline like chemistry, MSc. Okay, I think I partially agree on that. I do believe AI will revolutionize the way we're thinking, the way we're doing chemistry, accelerate everything. Replacing, I'm not so sure. Okay.
I would say that, you know, I do think of it as the student having to future-proof, or the old person like me, having to future-proof themselves, right? I am always trying to see where is there something new, and can I try to be at the forefront of that instead of, you know, the tide sweeping over me. I think it is going to change traditional disciplines, but, you know, we are I heard a wonderful answer. I went to something down at UCLA where people were talking about the future of work and AI and all kinds of things. And I happened to go to a humanities session, which I thought, well, there's not going to be that much here, and, you know, and stupid of me. It was the deepest session. So there was someone who got up and said, you know, my spouse knows I like a certain kind of music, and I like a certain singer, and I like particular songs. And she went and she had ChatGPT create, and I like jazz, and had somebody just create the most amazing thing for me that was better than anything I had ever heard. And you know, so what's going to happen to composers and musicians? And one of the humanists on the panel said, so that becomes the corpus. And what we always do is we advance the corpus, whatever the corpus is. The corpus has become a lot bigger. And so we can't know everything in the corpus. So what we have to do is know enough to take what is in that corpus and advance it in really interesting ways. So for me, that was a helpful view of it.
I want to add one quick note. It's true, students nowadays, my mentees, like they fear, like instead of becoming a first-class chemist, they become a second-class chemist and second-class AI scientist, and that leads to like not easy to find jobs in either field. So like I always tell them, it's like yes, you may have the same 4 years or 5 years, but it feels like you are doing 2 degrees. But in the end, like it would be worth it because you become like proficient in multiple disciplines, which gives you the opportunity for the new jobs being created in the new AI like related areas.
And I think in chemistry there are the corpus things, right? I mean, it's just we're doing stuff now, Omar, in ways that you had never imagined. And it's not just speeding up what's there. It's new ways of thinking about how one might create MOFs, right?
I think I just want to mention 2 quick things. I think her self-driving labs, again, allow non-chemists to do chemistry, okay? And that is transformative, right? Because the scope of workforce and so on changes. Now, what do you do as a chemist? You're in love with chemistry, you're in love with bonds and atoms and structures and reactions and so on. You have to start thinking, how do I add something novel to this? How do I break new grounds? How do I break a new way of thinking that I can be uniquely recognized for it? That's how you future-proof yourself. To do that, you have to cross disciplines, okay? And you can't wait for your PI to tell you to do that. You have to do it on your own.
Reinventing ourselves.
Okay, there's a question there.
Hi, thank you so much for the talk. Very interesting. I'm an undergraduate, and I just had a question for Pedong. So you mentioned that renewable energy is not free. I just want to talk about solar and question, like aside from the infrastructure costs, doesn't solar generate energy for free?
Solar energy is not free. Solar electricity, basically, I mean, nowadays, I think in California, the other day I was talking to some people from California Energy Commission. They are talking about by 2045, 100% our electricity will be renewable. Okay, we are on par to that. That just says it's 100% renewable, but the cost is still there. It's not free. Yes, sunlight is free. But installing the solar panel, the infrastructure, that costs money. Even though now the solar panel is very cheap, okay? But I mean, everybody hope that if the solar electricity is indeed 0 cents, then that solve all of our problem. But that's not going to happen, okay?
Okay, I am going to declare this a wrap. I would really, I'll hand this to Christian in a moment, but I would like to thank our incredible speaker panelists for a really wonderful session, and the earlier speakers too, but Christian will do that. Okay, thank you.
There are too many mics here now. So yes, let's thank first the first round of speakers, Gabe, Jeffrey, and Maria, and our moderator, Mark. So a round of applause. And then let's thank this session, Xiying, Pedong, and Omar, and our moderator, Jennifer. Okay, and with that, let me give you a little preview of tomorrow. So tomorrow morning, we will start with a session on foundation models. So we had this already discussed. We will have two experts, which will be, one is a local one, Teresa Head-Gordon, and the other one is a non-local one. What's the last name? Sani. Gabor Sani. I only know people by first name, as you see when I thank them. And then we have a second session on fire management. And in the afternoon, we'll go to more the applications and how you interact with funders. And we'll sort of, as I said very early, we need funders to help us to build climate resilient stuff, because we are academics, and eventually, if you want impact, you have to somehow get it out into the world. So this is a very important part, and the labs here are actually a wonderful partner for that. I'm really happy that we'll do that with them together. And with that, let me all invite you for the happy hour in the courtyard, where we can relax over a few drinks and discuss more. So see you morning at 8:30, right, Sarah? 8:30. So that's for Berkeley really early time.